Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video starts a series on indeterminate forms and the use of L'Hopital's rule for calculus, specifically a differential calculus course. And you're likely viewing this video because you're in the middle of graphing using calculus. And this is an odd topic. When you're in the middle of graphing, it seems like it just doesn't fit well. However, there is a big reason why we need to talk about indeterminate forms and why we need L'Hopital's rule. So let's start, and I'll tell you why in this video or maybe in a future video. But for right now, let's just start by having a conversation about indeterminate forms themselves. So let's rewind the tape a little bit to our pre-algebra days and ask, why is C over 0, where C is non-zero, called undefined? Why is that called undefined? And the reason is because technically division, or this notation that we have for division, let's say we have this notation right here. This is a shorthand notation for the following. This implies that C would equal A times B. That's really what this notation right here means. And in fact, that's how division is defined. That C divided by B is equal to A means that A times B is equal to C. Well, imagine that somebody comes in and says, okay, well then C over 0, I think that's some number A. Well, by definition of division, that would imply that C is equal to A times 0. But remember, we started with the statement that C itself is non-zero. So we have 0 times some number equaling a non-zero number. That cannot happen. So therefore, A cannot exist. In other words, A is undefined. That's why we say A is undefined, or in other words, that fraction here is undefined because there's no number that it can equal because C is non-zero. There's no number that you would multiply by 0 to become a non-zero number. That's why we call it undefined. Now, having that conversation before talking about indeterminate forms is sort of important, because then we can have this conversation. Well, what if C is 0? In other words, what if we have 0? Whoops, that was not supposed to be a highlighter. What if we have 0 over 0 equaling some number A? And we want that number A to be some concrete number, like 1 or 5 or something like that. Well, by the definition of division, this implies that that numerator should equal A times that denominator. Now, let me ask you a very simple question. What number would I multiply by 0 so that the product of that number and 0 becomes 0? And the answer to that question is you don't know, because there are an infinite amount of numbers whose product with 0 will become 0. So this fraction here, 0 over 0, we cannot determine its value. That is, it's indeterminate. And that's what we call an indeterminate form, because you cannot figure out exactly what that number is. There's an infinite number of answers that it could possibly be. So there's just not enough information to tell us what A is. And there are several indeterminate forms, and they all stem from that same style of question. The same, how do you figure this out? And we would say, well, we don't know. There's a ton of different ways to say that. So when trying to determine the value of a limit, we often arrive at ambiguous statements like the limit approaching infinity minus infinity or 0 over 0. For example, you could have a limit as, we'll do infinity over infinity. We'll have a limit as x is approaching infinity of, let's say, x squared over x to the third. Technically speaking, that would be infinity over infinity because the numerator is approaching infinity and the denominator is approaching infinity. As written, without us doing any type of algebra, that is an indeterminate form because it's infinity over infinity. Now, we can actually evaluate this just by dividing numerator and denominator by x squared, and we would find out very quickly that this is actually just the limit as x goes to infinity of 1 over x, and we know that tends to 0. But as it's originally written, it is hidden as an indeterminate form of infinity over infinity. And this is also to say that it is not true that if you have something like infinity over infinity, or a limit that's approaching infinity over infinity, that it will always be 0. Because I could write another limit that is approaching infinity over infinity, like x to the third over x squared, which again, you would have to agree, its numerator is approaching infinity, its denominator is also approaching infinity, and yet it's not going to be the same value as the previous example. Because if you do a little bit of algebra, you find that this reduces to x, and as x goes to infinity, well, so does x. And so here are two of the same styles of indeterminate forms, infinity over infinity, yet they lead to two different, completely different values, 0 and infinity. All right. In these cases, it is impossible to determine based upon methods of limits up to this point, other than algebra, I should say, to find the value or determine the value of these said limits. That is, these limits would be considered indeterminate. Again, you can actually find their values in these two cases just by doing a little bit of algebra. So we could actually find these values. But what if we can't do algebra? What if it's something like the limit as x goes to infinity of e to the x over x? There's no algebraic simplification that I can make there. So what do I do in that case? And that is, by the way, infinity over infinity. Well, before answering that question, we're going to spend a few moments just defining what the indeterminate forms are rigorously. So for the following definition, the function h that I have in that definition is typically just a combination of other functions. More specifically, h is going to be something like a ratio of functions, f of x over g of x, or a product of functions, f times g, or functions to functional powers like f to the g power, or it could be a sum or a difference of functions. And that's not an exhaustive list, but that's the most popular list. Okay, so here's the actual definition of an indeterminate form. If the limit as x goes to a of h of x approaches one of the following forms, then it's said to be indeterminate or have an indeterminate form. And the 7 forms are 1, 2, 3, 4, 5, 6, 7. Yeah, the 7 forms are as follows: 0 over 0, infinity over infinity, 0 times infinity. That is actually probably the most dangerous of all of them, because a lot of people, when they're working with calculus, they'll see a limit of a product of functions and they'll say, oh, the first function tends to 0 and 0 times anything is 0. That's not true. You don't know how quickly that object is approaching 0 and how quickly the other function is approaching infinity. And so that is probably the most dangerous one in all of the indeterminate forms. Another indeterminate form is infinity minus infinity, and then 0 to the 0th, 1 to the infinite, or infinity to the 0th. All of these, if they're within limits, are very difficult to determine their values just by eyeballing it or just by looking at it. You have something approaching 0 raised to something approaching the 0th power. There could be several different values that could take on. So again, hard to determine what these are. So we'll go ahead and create some limits having the indeterminate forms, and then we'll go ahead and try to evaluate some of them. Some of them we won't be able to evaluate, but maybe we can evaluate some. Who knows, right? It just depends on how we make them up. Let's see, the forms that we're going to deal with here are, I'm just looking back through. Okay, let's do the 0 over 0 form. So let's create a limit. And again, there goes my highlighter. Let's create a limit of something that approaches 0 over 0. And by the way, that doesn't mean the limit down here has to be 0. It could be 5, right? And so one example would be x minus 5 squared in the numerator. Obviously, that's approaching 0. And let's have something else approach 0, like let's do the natural log of 6 minus x. Now, as x approaches 5, that'll approach natural log of 1, which is 0. And as x approaches 5, the numerator will be 0 squared. So again, this is a 0 over 0 indeterminate form. Oops, that's 0 over 0 indeterminate form there. Sorry about that. That's 0. And this will be approaching 0 as well. So I didn't want you to assume that the limit had to approach 0, or that the x value had to approach 0. I just want my functions, whatever I'm taking the limit of, to approach the form 0 over 0. And in this case, there's no algebraic manipulation that you can do. You're stuck. There's nothing you can do here other than something we need to introduce called L'Hopital's rule. So let's go ahead and now try to find a form. So that was the 0 over 0. Let's try to do one that's infinity over infinity. So infinity over infinity, we actually just did, and I think the easiest way to create one of these is just to throw a function you know goes to infinity divided by a function you know goes to infinity. And there you go. That's infinity over infinity. By the way, infinity over infinity could be negative infinity over positive infinity, or negative infinity over negative infinity. Doesn't really matter what the signs are. What matters is that it's an infinite value over an infinite value. So again, this numerator is approaching infinity. The denominator is approaching infinity. So this is an indeterminate form of infinity over infinity. The next form that we talked about was 0 times infinity. And again, this I had said is the most dangerous of the forms because it's very enticing to say something about this. And I'm going to write this as, let's do it this way. Limit as x approaches infinity of 1 over x times e to the x. Now, technically, I could write this as just e to the x over x, right? But as I've written it here as a product, it is actually something approaching 0 times something approaching infinity. So it is indeterminate right now of form 0 times infinity. Yes, I could easily multiply those two things together to get e to the x over x to where it's now infinity over infinity. So that's just a little note, a preview of what we're going to be doing in the future. The next kind, which is infinity minus infinity, we have actually seen in our limits section of this course. You were dealing with a limit of something like, let's say, x squared plus 3x, and maybe minus x or something like that. That would be infinity because this is approaching infinity minus infinity. So it's infinity minus infinity. That's the indeterminate form there. And of course, we know what to do with that. With that one, you would multiply numerator and denominator by the conjugate. And so we have some experience with dealing with those. The last three are functions to functional power, or functions to functional powers, I should say. So like 0 to the 0th, and 1 to the infinite, and infinity to the 0th. And these are pretty okay to make up. Let's go ahead and do this. Let's have the limit as x approaches, let's have x approach infinity. And I'll have 1 over x raised to something, let's go e to the negative x power. Okay. So as x goes to infinity, the argument of that exponential, this guy right here, is approaching 0. And e to the negative x also approaches 0. So this is a 0 to the 0th power indeterminate form. Another indeterminate form, which we wrote down, there's 1 to the infinite. Again, making something up. We want something to approach 1. Let's have x approach, let's do 5 again. and we'll do the natural log of 6 minus x. So therefore, wait, nope, that won't work. Let's have x approach e. And we'll have the natural log of x. There we go. That'll approach 1. And I want to raise it to a power that'll approach infinity. Well, that'll be something like 1 over x minus e squared. That, as x approaches e, that denominator is approaching 0, but you're squaring it, so it's approaching 0 from the positive side, which means that exponent's actually approaching infinity. And so the exponent's approaching infinity, and as x approaches e, the natural log of x approaches 1. And so this is something like 1 to the infinite power. Again, no way to really evaluate this yet. And then the final one, infinity to the 0th power. An example of something like that would be, let's say x is approaching infinity of x raised to the, now I need something to approach 0, right? So we'll raise it to the 1 over x squared power. There you go. That is, again, a infinity. Let me go ahead and showcase that. That base is approaching infinity to the 0th power. The exponent's approaching the 0th power. So these are all kind of quick examples. We haven't evaluated anything, and that's okay. But in the next video, we'll start talking about a way to help us evaluate these. And we'll also talk about that question I posed earlier, which is why we're learning this in the middle of graphing functions using calculus.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.